the stress at sigma 1 and sigma 2, because sigma 1 and sigma 2 essentially represents the maximum and the minimum, right? Minimum stresses. Sigma 1 represents the minimum stress, or we should say that the minimum compressive stress, and sigma 2 represents the the maximum compressive stress. Now sigma 2 is essentially equal to P by A plus PE C1 by I, whereas sigma 1 is equal to P by A, which is the compressive stress, which is denoted by positive sign, minus PE C2 by I. And essentially our objective was to limit this sigma 1 to be only compressive stresses. And the sigma 1 will be compressive stress if PE C2 by I will be less than P by A. But it will be tensile stress if PE C2 by I is greater than P by A. Right. And we will not allow that. So let us put PE C2 by I to be greater than P by A. Right. Now I is equal to nothing but AR squared. So P by A, P by A, P by A, P by A cancels, and E C2 by R squared should be greater than 1. And if this condition is satisfied, then essentially what we have is the tensile stresses. But we cannot allow the tensile stresses. So what we do is that we will not put this greater. Instead, we will put this lesser, so that PEC2 by I is less than P by A, and essentially sigma 1 will be only compressive stress. So we will put this to be less than 1. I made a mistake, so I rectified it in a different way. Now the thing is, E should be less than, then therefore R squared by C2. And what is R squared? For a rectangular section, we know I is equal to, for this section it will be equal to, as bending will be induced about what axis? About this axis, or the YY axis. So effectively it will be equal to 1 by 12 B into H cube. 1 by 12 B into H cube. Right, and R squared is equal to divided by I by A, or BH. And essentially it will be then equal to 1 by 12 H squared. Right, and C1 is equal to C2 is nothing but is equal to H by 2. So essentially I put this here, and I will get E to be equal less than H squared by 12 by H by 2, or 2 by H. So essentially I have E is less than H by 6. Right. But if we put this force P on this side of the neutral axis, or on this side of the YY axis, then effectively what happens is that the same thing will be just reversed. The stress distribution will be some kind of a thing like this, wherein this will create some sort of a sagging moment then. And we know for a sagging moment, the top fibers will be under compression. So this fibers will be under compression, and this fibers will be under tension. And effectively, then we will see this point. So therefore, this, we should limit this thing also, right? So essentially, E is less than H by 6 and should be greater than minus H by 6, where minus is on this side of the YY axis, and plus is on this side of the YY axis. So effectively, if I have to make a synopsis, these are all derivations. If I have to make a synopsis, it's like this, that I have this as my short strut, and this, suppose, is my section, right? If I got to have a stress distribution wherein there will be zero tensile stress at this end, because if I place a load P here, it will have an eccentricity E, right? If I want to have zero tensile stress at this point, then effectively the stress distribution will be all compressive, right? And if I have to have this E, if this is, suppose, my H, then E should be less than H by 6, right? And if I put P on this side, and this is of eccentricity, suppose E, then E should be greater than minus H by 6. And if this is the negative direction of H, and this is the positive direction of H. In the next thing, what I will try to do basically, here what we are doing is that if this is my cross section and if this are the two axes, then effectively I am putting my loads across this